Hi, I'm Daniela Sadile, and this is the presentation of Group 3. This presentation is prepared by Eliza Cortez, Christian James Bibal, Marcos Juna Encabo, and Daniela Sadile. In this video, we will discuss instantaneous rate of change, optimization problems, and related rates. Instantaneous rate of change is the change in the rate at a certain time. It is the same as the slope of the tangent line at a specific point. Here's some examples so we can further understand this topic.
Instantaneous rate of change. First example. Consider the function f of x is equals to x cubed minus 2x squared plus x plus 1. We want to find the instantaneous rate of change of f of x at x is equals to 2. To do this, we first need to find the derivative of f of x, which gives us the instantaneous rate of change at any point. Using the power rule of differentiation, we can find the derivative of f of x as derivative of f of x is equals to 3x squared minus 4x plus 1. Now, we can find the instantaneous rate of change of f of x at x is equals to 2 by evaluating the derivative of f of 2 with respect to 2. The derivative of f of 2 is equals to 3 times 2 squared minus 4 times 2 plus 1 is equals to 12 minus 8 plus 1 is equals to 5. So, the instantaneous rate of change of f of x at x is equals to 2 is 5. Geometrically, this corresponds to the slope of the tangent line to the graph of f of x at x is equals to 2. This means that if we were to zoom in very closely on the graph of f of x at x is equals to 2, the graph would start to look more and more like a straight line with a slope of 5. The concept of instantaneous rate of change is particularly useful in physics and engineering, where it is used to describe the motion of objects and the behavior of physical systems.
Optimization problems aim to find solutions for the variables that minimize or maximize the objective function while satisfying the given conditions. Question 1. Consider that you have a rectangular piece of cardboard that is 12 inches by 16 inches in size. To create an open top box, cut 4 similar squares from the cardboard's corners and fold up the edges. What square dimension should be used to create a box that has the most volume? To solve this problem, we can follow these steps. Step 1. Identify the objective function. The objective is to maximize the volume of the box. The volume of a box is given by V is equals to LWH, where I is the length, W is the width, and H is the height. Second step. Identify the constraints. The cardboard has dimensions of 12 inches by 16 inches. And we need to cut out 4 identical squares from the corners. Let's call the side length of each squares x. Then the constraints are the width of the box after the corners are cut out is 16 minus 2x inches. The length of the box after the corners are cut out is 12 minus 2x inches. The height of the box is x inches. Formulate the step 3. Formulate the problem mathematically. We can write the volume of the box as V of x is equals to x, open close parenthesis, 16 minus 2x, open close parenthesis, 12 minus 2x. Step 4. Find the critical points. We can find the critical points of v of x by taking its derivative and setting it equal to 0. The first derivative of v of x can be written as v, this derivative of v of x is equals to negative 24x squared plus 336x minus 192 is equals to 0. Solving this equation, we get x equals to 1 inch, or x is equals to, or x equals to 7/3 inches. Step 5. Text for the maximum or minimum. We can use the second derivative test to determine whether each critical point corresponds to a maximum or a minimum. Evaluating the second derivative of v of x, we get second derivative of v of x is equals to negative 48x plus 336. At x equals to 1 inch, we have second derivative of v of 1 is equals to, can be written as, at x equals to 1 inch, we have v second derivative of 1 equals to 288, which is positive. This means that v of x has a local minimum at x equals 1. At x equals z/3 inches, we have v second derivative of 7/3 is equals to negative 16, which is negative. This means that v of x has a local maximum at x equals z/3. Step 6. Check the feasibility of the solution. The side length of each square must be less than or equal to half the width and half the length of the cardboard, which are 8 inches and 6 inches respectively. Therefore, the maximum value of x we can use is 3 inches. Step 7. Interpret the solution. The maximum volume of the box, which is obtained when each square has a side length of 7/3 inches, and the resulting box has a dimension 10 2/3 inches by 13 1/3 inches by 7/3 inches. That's all.
Suppose we want to build a rectangular pen for animals using 200 feet of fencing, and one side of the pen will be against the side of the barn, so something like this. And we want to find the dimension of the pen that will enclose the largest possible area. So inside here is the area, and outside this part is the length, this part is the width, and this part is the length again. So We can start by letting the length of the pen be represented by the variable L right here, and the width be represented by the variable W. And we know that the perimeter of the pen is 200 feet, so let's write it down. Perimeter is equal to 200 feet, like that, and that we only need to fence 3 sides, one equaling to W. And so therefore we can write an equation for the perimeter. 2L, so 2 length plus 1W equals to the perimeter 200. We can solve for W in terms of L, which give us W, which is equal to the perimeter 200 minus 2L, like that. So next we'll need to find the not need to find the area. This is the area, I guess. The area of the rectangular pen is given by A times LW. Then after we do this, we will need to substitute this here. So it's gonna be A equals L200 minus 2L, which is equal to A, which equals to, no, does not change, this A, 200L minus 2L squared. And next, to find the value of L that maximizes the area A, we can take the derivative of A with respect to L and set it equal to 0, like this. D of A is equals to D of L equaling to 200 minus 4L 4L equaling to 0. As I said before, we set it equal to 0. And solving for this, we simply have to divide this perimeter by this. So looking here, 200 divided by 4, I guess you can say that, or 4, which is equal to 50. Yeah. So yeah, that means that our L is equals to 50, and substituting the area for to get the W, you will simply need to do W is equal to 200 minus, let's put this here just to be safe, 250 or 52, whatever you want, is equals to 100, because 2 times 50 is 100 minus 200, which is equals to 100. That means that our W is equals to 100. And to confirm the fact that this value of L corresponds to a maximum area, we can take the second derivative of A with respect to L by like this: d2 A over dl, which is equal to here we can just take the derivative here, since this is the constant. This will be equal to 0, and this is the whole value, so for negative 4L. So here the second derivative of this first derivative is negative 4, and since the second derivative is here a negative, the second derivative, but since our second derivative is a negative, this confirms that the critical point we found corresponds to a maximum value of A. That is all.
Related rates. According to Wikipedia, it is finding a rate where a quantity changes by relating that quantity to other quantities whose rates of change are known or given. The rate of change is usually with respect to time. So, let's refer to this example. X squared plus y squared is equal to 25, where x is equal to 4, dx over dt is equal to 5. Find dy over dt. So when solving related rates, the first thing you need to do is to list down all the variables. It will make solving easier. So what are the variables here? Those are x, y, dx over dt, and dy over dt. The value of x is 4, y is unknown, dx dt is 5, and dy over dt is unknown. Then, to find the value of y, we will use Pythagorean theorem. So, x squared plus y squared is equal to 25. X is 4, so 4 squared plus y squared is equal to 25. 4 squared is 16 plus y squared is equal to 25. Then let's move 16 to the other side. Y squared is equal to 25. It will be negative 16, and y squared is equal to 9. Then y squared is equal to 9. Let's now find the y, the value of y. Let's square root both sides. So it will be y is equal to 3. But we found the squared value of y. So we're uncertain if the sign of 3 is positive or negative. So we have two answers. So it will be positive or negative 3. So now let's find the dy dt. Now dy dt, let's find first the dy dt of the positive value of y, which is positive 3. So to find dy dt, we need to find the derivatives of this. We need to differentiate. X squared plus y squared is equal to 25. So x squared, the derivative of x squared is 2 with respect to time. So the derivative with respect to time. So 2x with dx dt plus 2y dy dt, and the derivative of a constant is 0. So let's now substitute the values. 2x is 4, dx dt is 5, plus 2, y is equal to 3 this time, it's 3, and dy over dt is equal to 0. Then let's simplify. 5 times 4, 20 times 2 is 40, plus 6 dy over dt. So in order to find the dy over dt, we need to move the 40 to the other side, to the opposite side. So 6 dy over dt is equal to negative 40. Now let's divide both sides by 6 so we can cancel the 6 here. Divide both sides by 6. Now this negative 40 is indivisible by 6, so we'll divide both sides by 2, it will be negative 20 over 3. So the dy dt of the positive value of y, or the dy dt of positive 3 is negative 20 over 3. y is equal to 3, then it will be negative 20 over 3. Now let's try to find the dy dt of the negative 3. So this time our y is negative. So x squared plus y squared, 2x dx over dt plus 2y dy over dt is equal to 0. Then 2x is 4 and 5, then 2 negative 3, and it's still dy over dt is equal to 0. Then let's simplify. 40 plus negative 6. Negative 6 dy over dt is equal to 0. Then let's move 40 again to the opposite side. Negative 6 dy over dt is equal to negative 40. Divide both sides by negative 6. Then cancel. Divide by 2. It will be negative 20 over 3. Then it will be positive 20 over 3. So if y is equal to negative 3, then the dy dt is positive 20 over 3. So they're just the same, but the signs are different.